Okay, I did not get your exams graded, so I will have those. The Monday when we get back. I guess if you cannot live, you could email me and I could probably tell you what you get, but just remember you emailed me. If it's not what you like, but I will have them done when I get back, or when we get back. Okay, so here's where we left off in terms of Wednesday. So we said there were a couple things in terms of side reactions of the benzenes. Couple things to keep in mind. If the double bond's in conjugation with the ring, then that makes it more stable to be in conjugation with the ring, and that the benzylic carbon was a special position. So I left with the idea of, I've got carbon A and B here in this epoxide. Which carbon is the chloride going to add to? Is the chloride going to add to carbon A, B, or 50-50? Would be your choices. And we could make arguments on all three of them, so what would you think? Anybody want to make a case for any of them? Should I call on people, stress them out? Call on the people that aren't here listening to this right now? Shame on you. Anybody want to make a case for 50-50 A and B? I didn't say you had to support it, just make a case for it. What do you want to make a case for?
It's going to add to A.
You think the chlorine's going to add to A?
Yeah.
Why? Okay, does anybody else have does anybody want to argue for A? So it's closer to the ring, so it's more stable. Like the carbocation would be more stable. What kind of carbocation would that be? Here's what's the first step in this mechanism? Protonate the oxygen. So I'm going to protonate the oxygen to make the oxonium ion. And that's going to put the plus charge, but where's the plus charge going to go?
I think it's going to be like a delta positive on both A and B, and it's going to be more of a delta positive on the one that's closer to the benzene ring, so the Cl is going to go into the carbon A.
Okay, so did everybody hear that? The plus charge number 1 on the oxygen is not going to stay there. It's going to delocalize down into carbons A and B and form delta positive charges. You're saying the delta positive charge on carbon A is going to be greater than here because it's closer to the ring? All right.
Isn't it the strong like nucleophiles, such like the basic one attacks the least sterically hindered carbon.
Okay, so the nucleophile attacking the less sterically hindered one would be an argument for the chlorine to add to which carbon? B. Okay, so we've got an argument for A, we've got an argument for B. Anyone want to make an argument for A and B 50-50? No, really? What kind of carbon is A? Primary, secondary, and tertiary. What's B? Secondary. So they're both secondary. So you could make an argument that it's going to add 50-50 to A and B because both of those are secondary carbons with the same substitution pattern, except the ring. Now, with the delta positive charge being more on this carbon, what kind of carbon is that? The carbon next to the ring is a benzylic. It's the benzylic one, but it's analogous to the allylic one. So that's the only thing I would add to my argument, to your argument for A. So which one is it? True, they are both secondary. But really, when I use acid first, I'm going to form the delta positive charges. So basically, if the oxygen gets rid of all of its positive charge, or most of it, it's going to go down here to these two carbons. So the question is, where's the chloride going to attack? Under acidic conditions with an epoxide, where does the nucleophile add? To the carbon that is most, normally it would be most substituted, right? But that's 50-50. Let's take that a little bit deeper. The most substituted one usually had the greatest delta plus charge. So in this case, they have equal substitution patterns. Do they have equal delta positive charge? No, because the delta positive charge would be greater on carbon A, which is the benzylic one. Right? So we'll come back to the idea about opening this up with a strong nucleophile in a minute, because I would agree that if it's a strong nucleophile with no acid, it's going to go after the least hindered one.
I actually had a question, because when I learned about this, like, at the beginning, you said that, it's, functions like a carbocation, and it doesn't matter what groups are attached to it.
Right, as long as, so the dilemma that we had from on Wednesday was that a benzylic carbocation is going to be the most stable position. Apparently, except when it's against a tertiary. So I deliberately made this system so that it wasn't tertiary. So in this case, it's secondary versus secondary benzylic. And so in that case, the secondary benzylic would win. So, yeah, if it's secondary versus tertiary, that's not what we're finding in the lab, but I should probably shut up about that before I read it next week because somebody's stolen that idea. But when we open up an epoxide under acidic conditions, we basically put a full positive one charge between these two carbons, or a good chunk of positive one charge. The chlorine's going to add to the most substituted one, but really the most substituted one is the one with the greater delta positive charge. So in this case, it's going to add to the benzylic carbocation. Now, if you don't like that reasoning, then my suggestion would be swing the OH over to the right and write the carbocation. Swing the OH over to the left and write the carbocation. And what are you going to have? Secondary versus benzylic. But is that what happens? No, because if it swung over, you would get 50-50 cis-trans, and we know that the OH and the Cl will be 100% trans because that triangle stays in place. Okay, so in this case, the major product under acidic conditions would be to have the Cl add here, the OH there. So that would be the major product of the reaction. So like, what am I trying to accomplish here? Which is always a good question to ask. What I'm trying to do is, number one, review about epoxides, which we might need. But also the idea that the benzylic position is going to have the greater delta positive charge in this case. So acidic ring opening adds to the carbon with the most delta positive charge. In this case, it's going to be the benzylic one. So that shows the specialty, the special nature of the benzylic carbocation. Now, if I change that reaction, if I said, you know what, let's take that same epoxide, but now let's add Cl minus first, and then let's add H plus. Now what happens? This is strong nucleophile ring opening, and so where's the chloride going to attack? The least sterically hindered. Now again, you could say the one that is least substituted, but it's better to say least hindered. So the ring is a lot more hindered than the CH3, so the chloride's going to come in and add there, and then we break open the ring, the epoxide ring. So then we're going to end up with the O minus there, with the Cl down there, and then we just we'll add our H plus to give us our final product. So we can still control where the chloride goes by doing it under strong nucleophile or acidic conditions. But we got to think broader about substitution and really think about the stability of the carbocation, which is really what we're looking at. And then you could ask what would happen if there was another methyl group on the other side. So now I got secondary versus tertiary. I will almost guarantee you that at some point in the next 6 months we'll be doing that reaction to see where the chloride adds, to see which one of those two has the greatest delta positive charge. But since I can't buy it, we have to make it, and I'm not in the mood to make anything right at the moment. Although that would be easy, because I've already got the double bond, just need peroxy acid, some directions, some purification, some analysis to make sure it's what we want, and then we could open that up and we could see, do you get the same product there? Only the difficulty there is that I don't have the deuterium actually attaching to the carbon to tell me 100% where it went. So, but then again, I could use the Cl minus and we could see if it's the same. So we will eventually do that, I'm sure, to prove that. So this is this is the idea. So side chain reactions, what could we do? We can oxidize it, oxidize the alkyl groups with KMNO4 to make the benzoic acids, like we did in lab this week. I'm still trying to get rid of all the purple color from around the balances. I hate that experiment because every time I take a wet napkin and I start wiping, there's purple that keeps showing up. It's going to show up for the next 6 months until we're done, and then we're going to put more in there. So we did that. You can basically take your alkyl group, and you want to put the most stable product would be putting the double bond in conjugation with the ring, or forming a carbocation. And free radical halogenation is going to go to the benzylic position. So with side chain reactions, yes, I can invoke everything this year with those. But for the most part, we want to keep in mind double bond and conjugation is stable. The benzylic position is special. Okay. All right, so that's the side chains. Now what we're going to do is we're going to do reactions inside the benzene ring. But before we do that, there's one more kind of unique reaction that we should talk about, just kind of briefly, about taking a benzene ring and converting it into a non-benzene ring, destroying the aromaticity of that ring. Can you do that? Well, if you can't, then I should just erase it and we move on, but you can't. So why would you want to remove the aromaticity of the ring? I don't know. But you could basically take a benzene as your starting material and convert it into a cyclohexane or a cyclohexene. But this is going to take really harsh conditions because the benzene is aromatic and really, really stable. So in order to do this, this is what is called Birch reduction. And so Birch reduction is a very harsh reduction. And reduction in this case means, it actually means gain of electrons, it also means gain of hydrogens. So you take sodium metal and you dissolve it in liquid ammonia. And that sodium metal has one unpaired electron, and it basically loses that in the liquid ammonia to make a solvated electron. And you can't get any more reducing than to give something a naked electron. You're not transferring it from one to the other, you're giving it an electron. So this is a really powerful reducing reagent. You might say, well, couldn't you use like an electrode in a battery? This predates that. So when you put sodium or potassium into liquid ammonia, you get the solvated electron, which is going to add to the benzene ring. Now the mechanism for this is kind of outlined in a slide on the PowerPoints under the Birch reduction. I will just give you, well, first of all, I should say this is the second sodium liquid ammonia reaction that we've had this semester. I could ask you where you saw it before, but there would be a lot of page turning, a lot of giving up immediately. Sodium and liquid ammonia. It's an alkyne reaction. An alkyne gets sodium and NH3, and it becomes a transalkene. So that's where we've seen it before. And the mechanism for that is in one of the PowerPoint slides from before that, but the critical part of this whole mechanism is that when I add one unpaired electron to the benzene ring, I'm going to end up with a species that kind of looks like this. I'm going to end up with a pair of electrons on one carbon, and I'm going to end up with an unpaired electron there. So I'm going to end up with a radical anion, because the C with the lone pair is negatively charged. So what happens is that those two are big clouds of negative charge. They have to be as far away from each other as they can get. And in a six-membered ring, that means they're going to be 1,4. Each one of those clouds is going to pick up a hydrogen, which means that when I add my two hydrogens to the ring, both of those hydrogens are going to end up adding 1,4. So I'm going to make the unconjugated or the non-conjugated diene. Okay, this is not a mechanism that you're going to be responsible for, but I just show this intermediate, and if you looked at the mechanism, it might be able to help you out in a jam where you're like, oh, I can't remember, is it conjugated or not conjugated? The cloud's got to go as far away from each other as possible. And just to go back to this, that double bond came from, the trans double bond came from something that was very similar. That's why it was trans, is because the clouds got to get as far away from each other as possible. So what Birch reduction does is it lets you destroy an aromatic ring. So in theory, if all you had was an aromatic starting material and you wanted to make a cyclohexane or something out of it, you could do Birch reduction and get rid of the super stability of the benzene ring. It's just one of those reactions that's classically out there. Okay. So that's the first reaction inside the ring. But again, this is super harsh. I'm breaking up the aromatic ring. That is incredibly difficult. But this is the one way to do it. So now what we're going to do is now we're going to add electrophiles to the benzene ring. And we're going to work our way through these reactions now in the week after we get back. So let's add some sort of generic electrophile to a benzene ring. Now, just to remember, benzene ring is super stable because it's aromatic, and it does not react with CaMnO4 or bromine, just bromine, Br2. Doesn't react with HCl. So it's stable enough where it doesn't react with those reagents. But if I can make an E+, and it's got to be stronger than an H+. If I can make an E+, then I can add that to the ring. And then there's going to be a whole half a dozen or a dozen reagents on how to make that E+. So if I can make it, then let's talk about the mechanism. So first thing I'm going to do is I'm going to add use the double bond to add the electrophile to a carbon. And I'm going to add the electrophile to the carbon with the H on it. There's no Markovnikov or anti-Markovnikov here because I'm starting with the simplest case, which is benzene. We'll get more complicated. I can assure you we will do that. So that means that if I add the electrophile to that carbon, that gives me a carbocation. And the first thing I say is, what kind of carbocation is that? And you would say secondary and the other one, allylic. Secondary and allylic. So what did we do when we had allylic carbocations? We wrote their resonance structure. So let's do that again. Let's take this pair of electrons, move it here to now form the plus charge there and there. So we have a second resonance structure, and because this wasn't an allylic carbocation with just one double bond, it's got two double bonds, so I can do that again, and I can write the third resonance structure and put the plus charge there. Okay, so this is going to be the generic flushing. This is going to be the generic mechanism anytime I add an E+ to the ring. So all the E pluses we're going to learn today, and in the future, you just erase E+ from here, and you've got the mechanism. Let's write the resonance hybrid. So what would the resonance hybrid of this be? The resonance hybrid, we draw all of our single bonds in the molecule. Everywhere there's a positive charge, we're going to write a delta positive charge. Or if you want to, you can average out the charges on all the atoms. It'll be the same thing. And then the partial double bonds will end up basically going from one delta positive charge to the other. Connected bonds. Again, this is a pattern. This is sort of recognizing the pattern. I got that from averaging out every bond, every charge for each of the three atoms in the molecule. right? So there's my resonance hybrid. And this process of moving the pairs of electrons around to form the carbocation, we did something very similar to that with the benzylic carbocation last time to show that it was stable. Now, once I do that, something could happen, but it won't. In the past, a nucleophile has come in and added to each one of those carbocations. And then we've been into thermodynamic and kinetic products. The problem here is that if a chloride or a water comes in and adds to any one of those carbocations, what happened to the ring? It's no longer aromatic. It's no longer stable. So the ring is like, nope, that's not happening. You know what? I'm just going to take, and I'm going to lose my H plus and bring that pair of electrons over. And I'm going to lose H plus, and then I'm going to reform my aromatic ring. So what we're doing is not electrophilic addition, because that does not exist. Instead, we're doing substitution. What are we substituting? We're substituting one of the hydrogens on the ring for our electrophile. Does it matter which hydrogen? Not yet. Because we're just starting with benzene, so that any of those can be replaced. Okay. So the name of this reaction is electrophilic, aromatic substitution. And that's what the EAS stands for in the videos and in notes in Canvas. There is not electrophilic aromatic addition. That does not exist. There is a nucleophilic aromatic substitution, and we'll get to that in the future. But this is the most important one right at the moment. So I'm reforming the ring because it's going to become, it wants to be aromatic. So I'm going to do substitution. Everybody kind of with me? So if you think about how we got to this point, right? You take a step back, it's like, okay, how did we get here? And how we got here was, we talked about allylic carbocations and how to draw their resonance structures. And that's all we're doing here, except that we're going to lose a proton because we want to reform the ring. So there's a sequence of things that we've done. And all books that are still sold do that. Anytime somebody comes out with a brilliant idea to publish a new book under a new format, it's like, oh, that's a great book, and then it never sells. Because people don't want to go away from the traditional approach to organic, which is functional group, go up the line on functional groups, and build the topics on top of each other. The topics we're going to build on are electron donating and electron withdrawing groups. That's the next thing we're going to build on. So we'll talk about, well, what's the electron withdrawing group? What's the electron donating group? Rank them from number 1 to number 10. We've already ranked them from 1 to 9. There's a 10th one. And so we're going to have to know that, because right now, this is a piece of cake, sort of. I need to know what my reagents are and what E plus the reagents are generating. I just replace a hydrogen on the benzene ring. What if there's already a group there? Well, that's a little more complicated. Because if there's already a group on the ring, does that E go to the ortho position, the meta position, or the para position? And if it was just random, we would stop there and move on. It's not. Because what groups direct to ortho and para? Electron donating groups. What groups does the E plus add only in the meta position? Electron withdrawing groups. Right? So there is a method to madness. Right? There's always a method to the madness. You just may not see it for a while. Of course, there just may be madness with no method, but there is. There's a reason and a sequence of things. So now all we need to know is what are the specific reagents I can use to generate a bunch of different E plus groups and add them to the ring. And so, let's start on the dozen or so reagents that are going to do that. So if you're short 3x5 cards, it might be a good time to ask the Easter Bunny to get you more, if they still do that. The first one is, let's talk about halogens. Now the problem here is, that won't erase. There. The problem is that if I just add Br2, I'm not going to generate enough of the Br plus to add to the ring. When we reacted Br2 with the double bond, if you remember, it was Br attached to Br. The pair of electrons came from the double bond and kicked off the other bromine. One of the bromines became delta plus. That's good enough for a double bond. It is not good enough for a benzene ring because it's really stable. So I need to generate a pure Br plus. How do I do that? The classical way to do that is to take bromine or chlorine and react it with either FeBr3 or AlBr3. The more traditional way is to use aluminum tribromide, but iron tribromide also works very well. Okay. So that's a catalyst. So without the catalyst, this will be a no reaction. And you can replace all the bromines and put chlorines in there. What happens? What happens is that the aluminum or the bromine, the aluminum or the iron ends up taking a Br minus away. So the Br-Br bond truly breaks, and the Br minus goes over to form an AlBr4 minus overall. And that leaves a true Br plus on the other side. So it's like aluminum comes in and grabs the Br minus away. Same thing's true for iron as well. When we've done this reaction in the lab, I personally prefer iron tribromide because the iron tribromide, well, if it sits out in air, it goes from a purple color to a yellow color. The yellow color is the hydrate, which is bad. It won't work. So usually I have to get the bottle. I've got to mine my way down to the bottom to get all the purple stuff out because there's usually a 2-inch thick layer of yellow at the top. But if you use iron tribromide, it works great. Aluminum, it's hard to tell whether it's truly active or not. Because when it, as a colorless white solid, it turns into another colorless white solid. So you never know, you got to throw it in water and see if it explodes, and then you'll know it's good. It doesn't, it just fizzes very violently. So, easier to use the purple stuff. That's a way we can basically make a Br or a Cl+. Once I have that Br or Cl+, I'm just going to go ahead and substitute a halogen with a bromine or a chlorine. Bromine and chlorine, these reactions are interchangeable. Bromine's probably preferred because it's a liquid, so it's easier to handle, as opposed to chlorine that's a gas. So it's just easier from that perspective. So if you want to halogenate your ring, use iron or aluminum trihalide with the halogen. And that will do that reaction. So that's reaction number 1. Number 2 would be, let's say that we wanted to convert the benzene to a nitrobenzene. Okay, we talked about the nitro group being an electron withdrawing group. So, and as I'm putting these groups on there, it might be worthwhile to think about, well, what kind of group is that? Bromine is an electron withdrawing, nitro is an electron withdrawing. So if you want to make nitrobenzene out of benzene, what you're going to do is you're going to take nitric acid, mix it with sulfuric acid, and then what will happen is the sulfuric acid will protonate the HNO3. It'll lose water so that it basically forms the NO2 plus. So sulfuric and nitric acids are really good at forming the NO2 plus, which would then add to the benzene ring to give you nitrobenzene. The old, just as a aside to this, there's 2 asides to this that where nitros are added to things. The first is old movie film, right? The big ones that comes in the canisters. That's nitrocellulose. Cellulose from biology is what? A cotton ball. So I haven't done this. I don't know that I've ever done this, but Dr. Wayner does this a lot. Takes cotton balls and put them in a mixture of nitric and sulfuric acid for a while. You take them out, you wash them very thoroughly and carefully. You let them dry out, and then you take a cotton ball and put a match to it, and it's pretty boring. Right? It just catches on fire. Take a nitrocellulose cotton ball, and it's huge flame. So nitrocellulose is very flammable, and that's why preserving the old films, which they do somewhere probably out in California, they have to be careful because those can very easily catch on fire and all sorts of things. So nitrocellulose, that's something you can make. You have to be careful because it might explode by shock. So that's why you got to handle it carefully, I believe. The other thing you can nitrate is toluene. And we'll talk more about this reaction, but if I continually nitrate toluene, I'm going to put 3 nitro groups on it. We'll talk about the sequence of how you do that, but you make tri-nitro-toluene. Somebody said this morning, they're like the song? Do we know the song? AC/DC TNT? I'm like, I had to think about that for a minute. I'm like, oh, we're quoting AC/DC and 8 o'clock organic. Wow. But that is how you make the explosive. You can also, nitroglycerin is in putting nitro groups on a glycerin molecule. So those are slightly different. The nitroglycerin is actually what goes into the dynamite. You have to stabilize it with something so that it doesn't blow up in your hand. But like dynamite sticks, you put a fuse in, you light them, or you have that thing that pushes down and it blows the mountain up. That kind of stuff. Those nitro groups are used for those kinds of materials. So if you're going to make trinitrotoluene, number 1, don't. Number 2, you have to be really careful because the first nitro group goes on easy. The second one, you got to apply a little heat. And the third one, you got to apply just enough heat to get it to go on, but not enough to blow yourself up. Right? And this was a problem in the explosive industry. Who's the most famous explosive manufacturer? Alfred Nobel. And the reason why he gave all his money at the end was a few family members might have gotten blown up in the process. He is like sixth cousin, so many people removed from my great-great-grandfather. But if you have any kind of Swedish heritage, you would be related to Alfred Nobel. So that's as far as it goes. So we'll talk about that sequentially, how you can add groups. But nitro isn't nitro, and there's nitromethane you can use if you're like drag racing. They use those. So nitro groups, basically you have a gas molecule that when you burn it or when you heat it, it becomes a gas molecule, and that's why things are very powerful fuels. Okay. So we can put a nitro group on. What else can we put on? Well, we can put on what's called a sulfonic acid group, an S double bond O, OH group. That is a sulfonic acid. Sulfonic acid groups are relatively easy to make. You take sulfur trioxide and you add it to sulfuric acid, H2SO4. You make what's called fuming sulfuric acid. Fuming sulfuric acid, when you take the cap off of it, white smoke billows out, which is just the sulfur trioxide reacting with the moisture in the air to form little sulfuric acid droplets that are making a cloud of smoke. You know anything about acid rain, that happens up there, and then the acid rain comes down to Earth in very small quantities, small but detectable quantities. So sulfonic acids are used in a lot of things. If you have like a water softener, you might have a compound like that in there that will grab the calcium and magnesium from your water. Usually well water has high concentrations of calcium and magnesium. That makes the water hard. What does hard water mean? It means when you add soap to it, it forms a soap scum. Soft water doesn't do that. So those are kind of precursors to exchange the calcium for a sodium. So the sulfonic acids are used that way. We have seen something similar to, we've seen something like that where we had a methyl group here. We had an S double bond OCl that we used. That's again, given enough time, there would be flipping. That's the tosyl chloride. That's how you can make the tosyl chloride. That we use to react with an alcohol to make the alcohol a leaving group as the tosylate ester. I am legally obligated to ask you how we would get from the sulfonic acid to the tosyl chloride. What I heard is actually not going to work in this case. So HCl actually will not work. So we need an alternative to HCl. PCl3, PCl5, or SOCl2. So any of those reagents will work. Unfortunately, HCl will not. So PCl3, SOCl2, any of those non-HCl reagents will do this reaction. Right? I mean, we're nearly halfway through the semester. At this point, we have to be drawing in all of what we hopefully have learned. Or if you're like, oh my, I've forgotten all that stuff, keep it, get it back in there and keep it there. Right? So that's another group we can add, is the sulfonic acid group. Yeah, these are great groups, like nitro groups. If you want to blow things up, that's fine. But how about we just add an alkyl group? Well, if we think about this, in order to add an alkyl group to the ring, what do I need to make? A carbocation. So if I make a carbocation, that's an E+, that's going to add to the benzene ring. So how many different ways do we know to make carbocations? What ways don't we know? Take an alcohol. What are you going to add to it? Add H+. And you're going to get the carbocation in water. Where did the H+ come from? Something without a counterion to add to it. So, a weak nucleophile counterion. So, sulfuric acid. But wait, I thought H plus H2O did a dehydration reaction. H plus H2O and heat do the dehydration. If I just add H2SO4 in the alcohol, I can make the carbocation, and then hopefully it'll add the benzene. All right, you don't like that one? How about we add H+ to a double bond? What's going to happen? Markovnikov addition of the H+ to form then like a tertiary butyl carbocation. So our methods that we learned before about making carbocations is great because now we can add those carbocations to the benzene ring. Now, there's a little bit of a caution here. If I'm going to add something H plus to a double bond, do not use an aromatic solvent like benzene or toluene, because then that carbocation could add into the benzene ring. So you can't use those as solvents, but any of these methods that we use could be used to basically form isopropyl benzene, or could be used to form, in this case, tertiary-butyl benzene. And you're not going to like this, but one of the issues we're going to have to take up is, what about carbocation rearrangements? Well, they could occur too. So if I want to add a straight chain to the ring, I actually have to do something special, because otherwise that straight chain will do a hydrogen shift, rearrange, and I'll never add the straight chain to the ring. But we'll talk about that later. Okay, so these are methods we already know. How about new methods? All right. I want to pull the bromine off, and I want to make the carbocation. What should I do? You're not going to have to flip very many pages for this. What did I just use that rips a bromine away? FeBr3 or AlBr3. So this is called Friedel-Crafts Alkylation. At this point, terminology, I mean, we've had a lot of terminology, but I mean, it kind of makes sense. You're adding an alkyl group to something, it's an alkylation reaction. Friedel and Crafts put this together. One of my pet peeves is, this is Crafts, not like the cheese. Right? Ketone, the functional group ketone does not have a Y in it. Right? These are two things that are just kind of pet peeves of mine. But Friedel-Crafts alkylation would be, okay, take our alkyl halide, react it with, Friedel-Crafts traditionally would have been aluminum tribromide, but you could do the same thing. What are we going to end up doing? We're going to end up forming our carbocation, which is then going to add to the benzene ring, and we're going to end up with an isopropyl group. So the traditional way of adding alkyl groups to the ring is to do Friedel-Crafts alkylation. And then to go with this is Friedel-Crafts acylation, which we will talk about in the first couple minutes after we get back. So there won't be any quiz when we get back, although that's tempting. And then we'll just continue on. I'll be updating and putting the website, or putting where we're going to be at there on the website. So, all right. If you have any questions, I will be watching the computer because I'm not going anyplace fun. And trust me, this place ain't fun. But if you are, stay safe. Don't get coronavirus. Don't make any poor decisions along the way. And we will see you when we get back.